Okay, so we have just looked at the particle in the one-dimensional prison, and we realized that a solution like this was what we found as the general solution, and then we fixed the boundary condition. Then, given the boundary conditions, we were able to get rid of the b, and we only had the sign. But we could approach this more generally, and instead of fixing it in terms of sines and cosines, we could write the solution to the equation as a, we could leave them as complex exponentials, or e to the ikx plus b e to the minus ikx. These have a little more intuition in terms of waves, or the spatial part of a traveling one-dimensional wave. And in our case, remember that we have a one-dimensional prison between x equals 0 and x equals L. And so at x equals 0, we get e to the ik 0, and that's just 1. Same thing with this. This is 0, so e to the 0 is 1, so we get a plus b. That must be equal to 0, and this tells us that b is equal to minus a. And so psi at L gives us a e to the I k L. This is minus a e to the minus I k L. And this also has to be 0. And so this gives us that e to the I k L minus e to the minus ikl must be equal to 0. And of course, we can write these in terms of sines and cosines. This is just cosine of kl plus I sine of kl. And this is minus, this is a cosine of kl. So we get minus the cosine of kl. And then this part here has minus I, but there's a minus sign here, so that becomes plus I sine of KL, and this has to be 0. The cosines cancel, so we have 2I sine of KL equals 0, and we end up at the same boundary condition. So KL is equal to n pi, for that to be equal to 0. And the K is the quantity in front of the other side of the Schrodinger equation. So remember that our equation reads minus h bar squared over 2m, second derivative of the spatial part, is equal to e psi. And so the two derivatives of psi, of the spatial part of the wave function, is minus 2me over h bar squared times psi. And this quantity here is just k squared. So k squared is equal to 2me over h bar squared. Right, that just comes from e equals p squared over 2m. For the free particle, and p is h bar k, so we get h bar squared k squared over 2m, and hence that quantity, and so that's why the k is there. So let's go back briefly to the free particle, given what we've learned here, and look at the equation. It's the same equation for the free particle, right? So we can think of the solutions as being exactly the same as the solutions that we've found for the particle in the one-dimensional prison. So we could write something like this, sine kx plus b cosine kx, or we could write this as a e to the I kx plus b e to the minus I kx. But then we don't have any further constraints. We don't have the boundary conditions that can specify any further constraints. And so we know that these kinds of functions are not first of all, localizable, right? We can't localize the particle because these are just waves all the way to infinity in both directions. And there's no constraint on the energy. So it will turn out then when we get to so it turns out the free particle is actually harder than the particle that has some kind of constraint, like the particle in the one-dimensional prism. E is not constrained for the free particle, so it's actually not discrete. It can have a continuous range of values. So E is continuous. And in order to describe something physical, we'll have to figure out how to write in terms of these kinds of quantities. It'll be a continuous sum or an integral of these kinds of wave-like objects with continuous k that will describe some particle that, say, has some initial wave function. So if this is x and this is psi, that's a spatial wave function. Say at x equals 0, the particle is constructed in our laboratory, so it has an equal probability of being found in this region between x1 and x2 in this one-dimensional universe. But then it's free to move away from there after that. And we have no, again, discrete, no constraints on E, so E can be anything that we want. And so it's a much more complicated kind of thing, but the techniques are really the same kinds of things. We're going to get to continuous superpositions of wave-like objects. And so now we're going to learn a little bit more about these techniques by looking at discrete superpositions of these wave-like solutions for the particle in this constrained situation. And then we'll sort of look at situations where the constraints are a little bit weaker and the potentials are a little bit more realistic.